Hello there. So, if things have gone as planned in class earlier today, that would be Wednesday, we considered acid-base titrations after thinking about how we can make buffers by mixing a strong component like an acid with a weak component like a base, or vice versa, strong base with a weak acid. Then we saw the effect, or how a titration, or not a titration, how a buffer actually works by shifting the balance between the two components, weak conjugate acid and weak conjugate base, when a strong component is added into the system. And then we finished our class by considering titrations, because that adding an acid to a base is what we know to be a titration. So just to refresh your memory on that, here are the three types of acid-base titrations that we're considering. And in the video, this segment here, we're going to look at a few examples of the numerical considerations involved with acid-base titrations. But to refresh, we had strong acid, strong base titrations. pH begins very low, and then when we reach the equivalence point, the point when the moles of acid and base are equal to each other, there's a big spike in the pH. And then beyond that point, we just have excess base, so we have a very high pH for the rest of the titration time. Okay? The end point is the equivalence point, or end point, synonymous, is the case when the moles of base that we added are equal to the moles of acid that we started with, present initially. And we can use that to figure out a lot of times the concentration of one over the other. This is how you standardized sodium hydroxide, for example, in Chem 1 last semester. Okay? Sort of new now would be, what if one of the components is weak? A weak acid mixed with a strong base. Again, the pH would start out low, but as we titrate, given what we just saw earlier with some of our examples in class, some of the strong base converts weak acid into conjugate base, generating a buffer. And so we have this longer period for the titration where there's a buffer that's being built. And so we have to try to overcome the buffer. But still, once we reach the condition when the moles of base added perfectly equal the moles of acid that we started with, we'll see a spike in the pH, and beyond that point we'll have excess base, so we'll have a very high pH. What's an interesting point to add onto this is that at half of that condition, so this is our equivalence volume, our equivalence point, at half of that, the moles that we've added are only half of the moles of acid that we started with. So we actually have equal amounts of acid left over, weak acid, and conjugate base formed. In the Henderson-Hasselbalch equation, they'll cancel, and the pH equals the pKa. When you have an unknown acid, this becomes a way to help identify the acid, or with a base as well. In the case of a strong acid with a weak base, our pH now begins high. As we add the acid, the pH comes down. Makes sense when we add acid. When the moles of acid added equal the moles of base that we started with, we'll see that signature drop in pH, just like we saw signature spikes upward in pH over there. Now we'll see a drop in pH. That is our equivalence point. We could use it to figure out, how many moles of acid we've added, or how many moles of base were present, okay? If we know the concentrations. And then at half of that volume again, now we're going to have this condition where we've added an amount of acid that is half the amount of base. So we've turned half of our base into conjugate acid. We now have equal amounts of base and conjugate acid. They will reduce or cancel out in the Henderson-Hasselbalch equation, and the pH will still equal the pKa of the acidic part, the conjugate acid, that is, of the buffer that you've generated. And here would be your buffer region. Right? So conceptually, that's what's going on in our titrations. Let's dig into some of the numerical analysis that we need to be able to do with these acid-base titrations. So we did an example earlier when we made a buffer with hydrocyanic acid, HCN, and we added to it strong base sodium hydroxide. Let's consider that as part of a titration process. Instead of dumping all of the base in at once, what if we were incrementally adding the base to the acid? Well, we would generate a plot like we saw on this three graphs that I drew. In particular, it would have been the middle one with the signature buffer region as the weak acid is converted into conjugate base. All right. This will look fairly similar though. So what is the pH of a solution formed by adding 21.9 milliliters of 0.160 molar sodium hydroxide to 40 milliliters of 0.15 molar HCN. So as we so often need to do when we read a question, we need to identify the nature of the species with which we're working. So NaOH is a strong base, right? OH minus is the key to that there. And HCN is a weak acid. So the pattern in play here would be that the HCN would react with just the OH minus. Sodium's a spectator, not part of the chemistry that's happening here. This would form Cn minus and water. As a base, H2O is looking to gain a proton from our weak acid, right? That's going to leave Cn minus. Okay. Now in solving this problem, it is best if we work in mole quantities rather than concentration quantities, because not only do we have changes in the amounts of our materials, but we have changes in the volume of the entire system because we've mixed these two liquid solutions, two aqueous solutions together. So the table that I like to set up anytime I have a complete forward arrow to describe the reaction, that's how I know to do this. That's my sort of my red flag. Forward arrow means use a table with moles in it, okay? Because it will be a complete reaction. And I add a fourth row to that for concentration. So I'm working the first three rows in moles, the ice table that we're used to, but I'm working in moles, and I'm adding a fourth row of concentration. I always like to make a little note to myself, what's my volume after mixing? 40 plus 21.9 is 61.9 milliliters of volume. Okay? So moles, if you've forgotten, can be found by taking a solution's molarity times its volume. So for the HCN, this is going to be 0.00600. It's actually the same number of moles that we had in class when we considered making a buffer with this HCN. Intentionally chose that. For the OH, now taking the 21.9 and the 0.16, we have only 0.00350 moles. We have none of the conjugate base present. Now I said only 0.035 because this is a complete reaction, and that means that this is going to be the limiting reactant, the one that gets entirely used up. And so I know that all of the sodium hydroxide, or all of the hydroxide, is going to be eliminated because this reaction says take one HCN and one hydroxide and put them together. And so I'll do that until I run out of one or the other. In this case, I'll run out of the hydroxide. So I'll subtract that amount from each of my reactants and add it to my product side. So I will have 0.00250 moles left over of acid, and I'll have formed 0.00350 moles of base. And now I can figure out the concentration by taking the moles divided by this joint volume, 61.9. So I have 0.040 molar HCN. and 0.0565 molar for cyanide ion. Once I recognize a conjugate pair present in solution, I don't need to go any further. The pH is now equal to the pKa plus the log of the base, so that's Cn minus, over the acid. So the pKa would be the negative log of the Ka, which is 4.0 times 10 to the negative 10 for hydrocyanic acid, plus the log of the base, 0.0565, divided by the acid, 0.040. The pKa is 9.40, okay? And we've got more base than acid at this point, so we're raising the pH. This log term comes out to be plus 0.15, so the pH is 9.55. So this would be that one point, or just one point along the titration curve that we were looking at a little bit ago. Okay. Now I'm going to do a second example that follows up right after this one. In this example, I can tell that I have not yet passed the equivalence point because I haven't yet added enough OH to overwhelm the system. But what if I did? What if I added too much hydroxide and that sort of passed the equivalence point? So I'm going to calculate as a second example of this problem, what's the pH of the solution formed now by adding 39.3 milliliters of the sodium hydroxide. It's the only number I have to change to 39.3. So due to the magic of my board here, I've got the exact same reaction, so if you need to pause a second and write down the reaction, and I've actually got the exact same starting amount of HCN because I did not change the quantity and concentration of HCN. What does change into this problem though is the amount of moles of hydroxide now. I now have 0.00629 moles of hydroxide, and you can see that the HCN is now the limiting reactant. It's the smaller quantity of the two. So you want to be on the lookout for that. You're going to do many problems where the weak component is the excess reactant and the strong is the limiting reactant, but it doesn't mean that it can't happen this way where now the strong component is excess and the weak is limiting. So you have to pay attention to the numbers actually. So we will subtract the 0.0060, the limiting quantity, and add it on the product side. So I won't have any of my weak acid left, and I'll have 0.00029 moles of OH and 0.00600 moles of Cn minus. Now, unlike the case that I just erased, this is not a conjugate pair. So I cannot use the Henderson-Hasselbalch equation. So what am I going to do? Well, I'm going to remember the easy, obvious stuff that we learned earlier with acids and bases. I'm staring at a number here underneath hydroxide. If I turn this into a concentration, my total volume, by the way, was 79.3 milliliters, adding that 40 and 39.3. My hydroxide concentration is 0.00366 molar. All right? And if you know the hydroxide ion concentration, by default, you know the hydronium ion concentration, and thus the pH. Or perhaps a little more easily, we know the pOH from the OH concentration. So this is actually a little benefit of adding too much OH, in the calculations at least. It becomes a little easier to get to the pH a little bit faster. So 0.00366. So my POH is 2.437. And thus my pH found by subtracting from 14 is going to be 11.563. Okay? It's highly basic because we added too much base to our weak acid. We went past the point of equivalence. So in that titration curve that I drew a little bit ago, the first example that we did would have been somewhere around here. I could tell I was past the half equivalence point because the moles of OH were bigger than half the moles of acid. And this example that we just did would be up here near the top, where we've far exceeded the moles of acid and we've gone beyond the equivalence point altogether. All right? So let's do a couple more of these. Let's try a weak base being reacted with a strong acid in the next two examples. So, what is the pH of a solution formed by adding 13.6 milliliters of 0.17 molar hydrochloric acid to 30.0 milliliters of 0.160 molar nicotine? Now, nicotine is a weak base. We could look this up. It is on our Ka chart. Nicotine is a weak base whose Kb is 7.0 times 10 to the negative 7, I believe. At least that's what I am working off on my sheet right here. Okay? So our reaction is different this time. If we identify the nature of our substances, we have nicotine, which is a base, plus a strong acid. HCl, remember, is really H3O because it dissociates HCl completely, and all of the H's get picked up by waters. So it's H3O. But as a strong acid, that's going to indicate a forward complete reaction. We will form the conjugate acid of nicotine, the nicotinium ion, and then we would have some water left over as well. Now, we have a forward reaction, so we will solve this problem with a reaction table using moles. So I've got moles initial, change in moles, and my final moles, and then my concentration row. My concentration, my total volume, when I go to calculate that, is the sum of the two, 30 and 13.6, so 43.6 milliliters. Okay? Now, just like we did last time, molarity times volume gives us our moles. So for our nicotine, 30 milliliters, 0.16, we've got 0.00480 moles of nicotine. We've got 0.00231 moles of acid, and there's none of this present at the start. Which is our limiting reagent? The acid, smaller amount. So it becomes the one that we subtract. All of the acid will be used up. Add it to the nicotinium column. I mean, none of that H3O plus left. Okay? Boy, if we had added too much acid, like the problem we just did with the base, this would be very straightforward. We'd have excess acid, then we could get the pH directly from its concentration. But here, all of this is consumed, so the pH is going to depend on the balance of weak components, conjugate acid and weak base. So under the nicotine, I have 0.00249 moles left. And of course, I've got 0.00231 moles of conjugate acid formed. So if I divide by the combined volume now, my concentration is 0.0571 for the base, and 0.0530 for the conjugate acid. I have a conjugate pair, right? Because my numbers are underneath the two things that are separated by only a hydrogen. That's how I know I've got a conjugate pair. So the pH will come from the Henderson-Hasselbalch equation. And despite the fact that this is the titration of a weak base, the pH is still calculated as pKa plus the log of the base, so this would be the nicotine, divided by the acid, the nicotinium. Okay? Unless you want to learn a second equation, trust me, just use the Henderson-Hasselbalch equation in this fashion here. Now what this does mean is we have to figure out the pKa of the nicotinium ion. So if I hop over here, my Kb would lead me to the pKb, right? The negative log of this value. So the pKb of nicotine is 6.15. So the pKa would be 14 minus that pKb, because a conjugate pair, the sum of pKa and pKb is 14. So the pKa is 7.85 for the nicotinium ion. So I can just use that number here, 7.85 plus. Okay, the video briefly cut off there, sorry. Just calculated that the pKa of the nicotinium ion is 7.85, so we're ready to use that in our pH calculation in the Henderson-Hasselbalch equation. So 7.85 plus the log of the nicotine concentration, 0.0571, divided by the nicotinium, conjugate acid, 0.0530. We have more base than acid, so that's going to be raising our pH, but not by much. These are pretty close. This ends up being only 0.03, and we get a pH of 7.88 for this, this point in the titration. All right. Now, I could do an example where I exceed the end point, like I did with the hydroxide and the HCN, but that really isn't much new. Let me show you one other type of new problem relating to this titration that I'm looking at right here, so that we can make some use of the information that we've already got on the board. Okay? So the problem, I'm going to need the reaction to stay up there. But this problem is going to talk about the end point, the equivalence point of the titration. So my question here is sort of twofold, because even if it was only asked in one part, you'd need to do two things. So first, what volume of HCl is needed to reach the equivalence point of the titration in the previous example? And then secondly, what is the pH at the equivalence point? Okay, so a couple of different things going on here. So at the equivalence point, that's the key here. What do we know? From the, in each of the cases that I listed earlier, regardless of what style of titration it was, strong acid, strong base, strong acid, weak acid, strong base, the equivalence point was always defined for a 1-to-1 titration, which this is, 1 mole of base and 1 mole of acid combined, all right? As the condition when the moles of acid present equal the moles of base present. Because both of these are in a solution, we can use MAVA to represent the moles of acid then, because that would tell us how many moles of acid we have, equals MBVB. Again, how many moles of base we have. Well, we know the molarity of our nicotine base solution. It's 0.160 molar. And we used, in the previous example, I just erased it, 30 milliliters. And the molarity of our acid is 0.17 molar. So therefore, the only unknown is the volume of the acid. That's what we're after. How much, what volume of acid do we need to reach this equivalence point? So if I divide the 0.17, what I'm really doing is VA is going to be MBVB divided by MA. I will get a volume of 28.2 milliliters. So now the question really is, what is the pH, and we can treat it just like the former example, what is the pH when we add 28.2 milliliters of the acid? All right. Well, if we set out to solve this in the same manner, I could set up the exact same reaction. The reaction's still nicotine and strong acid, right? I have the same 0.0480 moles of nicotine that I had before. But now I have an identical 0.0048 moles of acid. So neither or both are the limiting reactant, right? We're going to use up all of the nicotine and all of the hydrochloric acid. And we'll form an equal 0.00480 moles of the conjugate acid. So we'll have none of this left, none of this left. Okay? Our total volume, though, will be the 30 that we started with, plus the 28.2 to reach the equivalence point, so 58.2 milliliters. So we'll have 0.00480 moles of nicotinium in 58.2 milliliters of volume for a concentration of 0.0825 molar. So again, this is not a conjugate pair. So we can't use the Henderson-Hasselbalch equation, but it's also not like the earlier case where we had an excess of hydroxide, and we don't have an excess of the strong component here. What is this? This is a weak acid in water. Look at that. That's what it is. It's a weak acid in water. And so we're going to use the exact same skills that we learned in chapter 15 to describe this. This is an equilibrium reaction now, right? Because nicotinium is a weak acid, and it makes NiC and H3O+. Boy, it looks exactly like this reaction in reverse, but now it's considering this as a reactant, weakly donating a proton to water. So I can now set up my table the traditional way using concentrations, okay, to give me the equilibrium concentrations. And the ending number from the first calculation becomes the starting concentration of my nicotinium ion. Disregard water, don't do anything with that, and I have 0 of these two. So I've really just taken this line and flipped it into this problem over here. Considering that this is a weak equilibrium and we're trying to figure out now how much of this reacts, we're back to not knowing, like we did with our examples up to this point in the video and class, but rather some of the nicotinium reacts. So we use minus X plus X plus X. So we have 0.0825 minus X, but X, whether we ignore it or not, will depend on the Ka of this reaction. So we need the Ka. Now earlier the Kb of nicotine was 7.0 times 10 to the 7. The Ka, well, actually let's save some time. The pKa of nicotinium was 7.85. Therefore, the Ka is 10 to the negative pKa, and that is going to be 10 to the negative 7.85, or 1.43 times 10 to the negative 8. A very small Ka, meaning we can approximate this as just 0.0825, like we're so used to doing. And then these, of course, will be x's. There's nothing to ignore them in relation to. So the Ka of this problem would have the nicotine base times the H3O plus divided by the nicotinium ion. So 1.43 times 10 to the negative 8 equals x squared over 0.0825. This should look pretty familiar, right? We've solved a number of problems like this. We take the 0.0825 over to the left, take the square root. X is 3.43 times 10 to the negative 5. This is, among the two things of interest to us, it is the concentration of H3O at equilibrium. All right? And so how do we end this problem? pH is equal to the negative log of this value. So the pH is 4.46. Does that value make sense? Yes, because the equivalence point has a pH that is below 7 for a strong acid, weak base titration. For this very reason, at the equivalence point, the strong component and the weak base completely cancel one another out. We're left with weak acid in water. Weak acid in water will always generate some H3O, lowering the pH below 7. All right? And so it's an interesting case. A strong base, weak acid titration, just the opposite. You'll have conjugate base left over. That's going to generate some OH and raise the pH. So I've walked you through several examples, and I've passed out a sheet in class that has additional titration examples where I work you through it with some guidance and a couple of practice ones at the end. It's a great set of problems that you should be well on your way to completing all the Mastering Chem problems that are associated with acid-base titrations. At this point, there's just one topic left in Chapter 16, which we'll pick up in class on Friday, and I will see you then.